Sometimes in life, we encounter things that are so unexpected and unintuitive that we describe them as magic. That must have been how lightning seemed until a summer day in 1752, when our school's founder, Benjamin Franklin, bottled lightning in a Leyden jar using a kite. Today, I'd like to tell you the story of another form of magic that we've encountered in the field of condensed matter physics over the last decade. This is magic angle twisted bialar graphene and the magical many-particle physics that we see in these types of systems. Yeah, so we're all here because we're PhD students and we want to shine light on some particular area in some system. And we want to illuminate what is going on there. And I'm looking at material science, like two of the presenters before us. And the goal of all this is to improve the quality of life through new properties and new materials. Walking here through the Penn Museum, you pass by a stone sphinx and many bronze and iron artifacts. And perhaps someday, in the distant future, you might pass by silicon artifacts, all indicative of the age that we're in and the era in our society. Through new materials, we enable the properties of our life and thus what our society is capable of. 2 blocks away from here, the first digital computer was created. But when you compare that to the simplest, cheapest calculator you could buy today, it pales in comparison. That's because we've mastered the physics of silicon. Silicon is governed by single particle quantum mechanics, and through its structure and its outer valence shell, we can understand its behavior entirely. So it's natural to ask, what is next? And within the realm of single particle quantum mechanics, it may be possible to create devices that have much longer lives between getting plugged in than we currently have. And that's what topology may give us from the lens of Kane, Mealy, and others here at Penn. But on the many-particle side, superconductivity may be hugely beneficial. 10% of the electricity that's generated at a power plant never makes it to the consumer because it's dissipated in wires. And Schrieffer was one of the first people who explained this, and he too was a faculty at Penn. Looking to the future, many-body quantum simulators and computers may help us to understand and generate new molecules and revolutionize the world of finance and optimization. So how do we get to this? Well, energy we usually think of in terms of motion, but also in terms of position, where things are. But if you can quench that motion energy, then you can get something that's entirely dictated by the interactions. And that's precisely the limit we want. That of interacting electrons leading to interesting states. And this is magic angle twisted bialar graphene. Starting with the pencil lead, placing it together with a subtle twist. That can quench the kinetic energy. And that can lead to interesting states with fractionalized excitations, separation of spin and charge, unusual superconductivity, and other building blocks that can be used to create new devices. So here we see a paradigmatic example where you twist these two systems, red for the top layer, blue for the bottom layer. And then at a certain twist angle, all of the kinetic energy for some of the electrons vanishes. Then you can realize these interesting interacting states. But this doesn't last over a long length scale. It only lasts over a couple microns, and device reliability is pretty low. So is there a better way to get to this? And that's what I'd like to introduce in this talk, which is that people have only been considering what happens in stacks of these materials, but not when you interface them with a broader whole. What happens when you start to tunnel electrons into or out of the system, or if local information decoheres? When you start hybridizing with a substrate, that can then enable new physics and new physical behaviors, and in particular, some of these flat bands. In cosmology, we think of dark matter as something that we can't observe. We know it's out there because of its gravitational effects. Here, we're going to talk about dark states because they can't be measured by the substrate, even if they're hybridized by it. So if we can put electrons into those states, then they can live and interact in them without being decohered, and the information can be stored long term. So here, in a paper I published last year with faculty member Martin Klassen here, we see that the bandwidth, the dashed line, drops to 0 above a certain coupling between your system and your substrate. This corresponds to forming the flat bands, but the blue region up here corresponds to long-lived states. There are many long-lived states that you could have with completely dispersionless bands without having to worry about a twist. So you get to that magic of the flat band and its interacting physics without having to worry about a twist. So this is perhaps a way to revolutionize new quantum devices, leveraging many-body physics. So we've seen that mastering materials defines our era, as indicative at the Penn Museum. And my work is to look into how can we get new electronic states that interact and work together to form a more cohesive whole and create the building blocks for new technologies. Thank you.